Analyzing a CPM problem relies on drawing a network. This particular scenario is a good example of that. Let's take a look. Considering the following project, which consists of 10 tasks. There's a list of 10 tasks, how long each will take, and their immediate predecessors. And then right away, we start with questions. What is the critical path through this network? What is the completion time of this project? This is a typical CPM problem, and you can tell because of the 3 pieces of information. Some stuff to do, how long each takes, and in what particular order. Now, the questions that start right away, what is the critical path through this network? We can't get any farther with those questions until we draw the network. Okay, now I'm waving a pencil around. Always draw networks in pencil. You never really know when you're starting out exactly how you will want the network to appear. So, begin with a pencil, you can erase. Let's see, we begin drawing a network by drawing its start. This represents the start of the project. Now, what do I draw next? I draw or illustrate, that's another way to think about it, any task that doesn't have any immediate predecessors, and I can see right away that that's tasks A and B, because these are the tasks that can be done at the start of the project, which means they belong near here on the network. Okay, so let me scoot down here and draw a node, if you will, a table, a symbol that represents task A, and then one likewise that represents task B, and connect. From the start, you may proceed to either of these 2 tasks. Okay, now working my way down the list. I notice up here that tasks C, D, and E all have A as an immediate predecessor. I'm going to draw that. Okay. When you're done with A, you could proceed to C, to D, or to E. Let me draw the arcs or arrows that represent us proceeding from the finish of one task to the start of another. Oh, okay, C, D, and E are in our illustration. Now our illustration will be finished when they're all there. Let's see, who's next? F. F has C as an immediate predecessor. Well, C is up here, so let me just draw F after it. F. When you're done with C, you can proceed to F. And then G has E as an immediate predecessor. G has E. Well, here's E. Very similar. When you're done with E, proceed to G. Then H has B and E as immediate predecessors. B and E. Okay, here's B, here's E, so let me draw H somewhere nearby. And connect. This is done, and that is done. When they're both done, you can begin with this. All right, I has H as an immediate predecessor, so we just drew H. Move over, draw I. And then J has F, G, and I. Okay, here's F, there's G, there's I. I will draw J, and then I connect. Okay, that means that connects, and essentially that connects. Now, at this point, with this sketch, I have a representation of each of the tasks. I'm not finished with the network though, because a good project network, a good CPM network, will have one start and one finish, representing this is it, this is the end of the project. So I need to draw that, right? Oh, so I pick a point over here and I say, okay, this is the finish. Now what I want to do is I want to connect every task in my sketch that has arrows pointing at it, but right now there's no way to escape it, so to speak. So for instance, you notice that J is that way. There's arrows pointing in, but there's no way right now to get out, so to speak. That means that it is connected to the finish. It must be like one of those last things that's done just before the finish. There's no tasks after it. Okay, so J needs to be connected, not a problem. Everybody else, it looks like there's a way out except for, now notice this, except for D. You know, when I drew all the precedence relationships, D just stayed embedded in this diagram, and there's no way out. So D needs to be connected to the finish. You say, oh, okay, no big deal. Except that, the way the network's drawn right now, the way I naturally drew it, to connect D to the finish, I'd have to draw over, I would have to cross another arc. That's bad craftsmanship. Now, strictly speaking, you could do that, and if you were very, very careful, probably later none of your computations would get messed up, but there's always a chance. So we really, I said good craftsmanship, really don't want to do that. We don't want to cross arcs if we don't have to. And we say, well, what do you mean by we don't have to? Well, I'm noticing that if I had just drawn part of this network a little differently, I wouldn't have to. For instance, if I had just said D, C, and then E, right? D would have wound up out here, wouldn't have gotten embedded. Oh, it wouldn't be that hard to fix. That's why we did this in pencil. Okay, let me undo this. I'm going to put it back, but let me undo F. The reason I did that is I want to change the identities of these two tasks. I don't want the top one to be C and the next one to be D. I want the top one to be D so it doesn't get trapped in all that mess. And then the central one to be C. And I had to erase F because it was kind of awkward. This would be a better place for it now, right? I'm just redrawing what was there. First you do C and then you go on to F, and then F was connected to J. So in a certain sense I kind of took F and I also moved it down a little bit. Now D, there's nothing blocking it from the finish. That's really what I was after in adjusting the network. Okay, that is a better network in terms of craftsmanship. Oh, all right. Now, well, now we just have a picture of the network. We're still working on that first question. What is the critical path through the project? It says, what is the completion time of the project? Actually, that second question we will be able to answer before the first one. But at any rate, we can't answer either one of them until we do some computations concerning timing, which means I need to add some detail to this network. First off, I'm going to do the division that's helpful within these symbols by dividing it into 2 rows and 2 columns, 1 skinny column and 1 lengthy column. This is just a helpful format for storing all of our information. Because, okay, next step, let's add the completion time data to the network. Okay, we haven't done any computations, but up here, I noticed that, for instance, A is 6 days long. This is the symbol that represents task A. Just note a 6 there. That's 6 days long. B is 2 days long. C, now careful, C is this one now, is 3 days long. D is 5 days long. E is 3 days long. F is 2 days long. G is 3 days long. H is 4 days long. I's down here is 2 days long, and J is 2 days long. Okay, now I didn't do any calculations, I only recopied the data. Now it's time to do some calculations. To find the completion time and the first step in finding the critical path, we need to find the early start, early finish times of each one of these tasks. Okay, you find early start, early finish times by going to the starting node and finding all the tasks that are connected with the starting node, so to speak. Oh, okay, they're A and B. Right, A and B automatically have early start times of 0 because There's nothing stopping you from starting work on either one of these right now, and right now on a number line is 0. Okay, now in the case of A, the early start time is 0. It's 6 days worth of work. That means the very earliest you could be finished with this is in 6 days, just logically. B, you start on it right now, 0. 0 plus 2, the earliest you'll be done is in 2 days. Now, let's work our way through the network. For instance, back to D and C and E. Each one of these tasks is waiting for A to finish. That's what the network says. Okay, that means that if A could finish at the earliest in 6 days, you can pass that number forward. That is the earliest you could possibly start on any one of these 3 tasks, is in 6 days. Okay, so in the case of D, the early start time is 6. 6 plus 5 is 11. Its early finish time is 11. In the case of C, 6 plus 3, the earliest you could possibly finish with that one is in 9 days. In the case of E, same thing, 6 plus 3, at the earliest you'd be finished in 9 days. So we're just using a little bit of arithmetic here. You know, the early finish time, just logically of a task, is its early start time plus the task time. All right, now, here's an easy one. F is just waiting on C to finish. C could finish now, we know, at the earliest in 9 days. Pass the number over. That means that F could start at the earliest in 9 days. 9 plus 2 is 11. Now, who else? G. G's another pretty straightforward one in that it's just waiting for E to finish, right? Okay, E will finish at the earliest in 9 days. 9 plus 3 is 12. The early finish time for G is 12. Now, we're done with this step when we have done this for each of the tasks. Let's look at H. Okay, H is only a little more complicated. H has 2 immediate predecessors. I see 2 arrows pointing at it. H cannot start until B and E both finish. What we now know is that B will finish at the earliest 2 days from now, and E will finish at the earliest 9 days from now. So what is the very earliest we could possibly start on H? That would be 9 days from now. Also known as the early start time rule. The early start time for an activity is equal to the largest of the early finish times of all activities that precede it. When we were doing the easy ones, we were doing tasks in which there was only one immediate predecessor, so there's only one number, right, to pass. But you do have to be a little more careful with tasks like H that have more than one immediate predecessor. Always pick the largest of the early finish times there. Okay, so anyway, H, the early start time is 9. 9 plus 4 means its early finish time is 13. I is another so-called easy one in that it's only waiting on H, so you can just pass the number over. I could start at the earliest in 13 days. 13 plus 2 is 15. There's only one other one to do here. And that does take a little logic. J is waiting on F, G, and I to finish. F will finish at the earliest in 11 days, G at the earliest in 12 days, and I at the earliest in 15 days. The early start time rule says we have to pick the largest. We're waiting on I to finish. Okay, so if I finishes at the earliest in 15 days, J could start at the earliest in 15 days. 15 plus 2 is 17. We have finished the early start, early finish timings. And at this point, we could actually answer that second question. It says, what's the completion time of this project? Now that we've filled these in, what you do is go to the finish node here and trace any arrows back. What activities are attached, so to speak, to the finishing node? Well, J and D. Look at their early finish times. These are the last things that will be done on the project. D could be finished up at the earliest in 11 days, and J could be finished up at the earliest in 17 days. We now know the expected completion time of the project, 17 days. Again, you pick the largest, right? What's the last thing to finish? Okay, so the expected completion time of the project is 17 days. Good. We have that question answered. The critical path of the project, though, we're going to have to find the late start, late finish times to reveal that. The late start, late finish times actually do begin with that fact, 17 days. We've determined that the completion time of the project is 17 days. That becomes our deadline. We declare that we will be done in 17 days. That means that, again, return to the finish node. Here, look at everybody attached to the finishing node, so to speak, the last of the tasks. Take that 17 and make that their late finish times. Because to find late start, late finish times, we do the reflection, like almost the opposite of what we were doing earlier. We start at the finish node and we're going to work our way back towards the start. We start at the finish node by declaring that 17 is our new deadline, so that anything that comes at the end of the project at the very latest must be finished in 17 days. Oh, all right, so look at D. If D at the latest must be finished in 17 days, and it's 5 days worth of work, 17 minus 5 means that the latest that you can get started on this without creating delays is in 12 days. Versus J, 17 minus 2, the late start time for J is 15 days. Oh, this is also arithmetic, right? Late start time equals late finish time minus task time. All right, now let's start reasoning our way back through the network. We now know that J has to start at the latest in 15 days. J cannot start until F, G, and I finish. So take this number and pass it back. That's their new deadline. At the latest, F has to finish in 15 days. At the latest, G has to finish in 15 days. And at the latest, I has to finish in 15 days, because if they don't, they'll delay J and they'll mess everything up. All right, now, in the case of F, 15 minus 2, that means at the earliest it's got to get started in 13 days. In the case of G, 15 minus 3, what's that, 12? G has to start at the latest in 12 days. In the case of I, 15 minus 2 is 13. Its late start time is 13. Now let's keep working our way back through the network. All right, I'm looking at F. F cannot start until C finishes. F, we now know, has to start at the latest in 13 days. You could just pass that number back. That means that C has to finish at the latest in 13 days to not hold it up. 13 minus 3 is 10, so the late start time for the task called C is 10 days from now. Who else can we do here? Oh, I, we know, also actually has to start at the latest in 13 days. It's waiting on H. There's another case you could just pass it straight back. Okay, the late finish time for H then is 13. 13 minus 4, its late start time is 9. We are working our way back through the network. Now H has 2 tasks before it. H has 2 tasks before it, meaning it has 2 immediate predecessors. It cannot get started until these finish. Oh, now let me think. E, though, E has to come after. E has to come before H, and E has to come before G. So while H, I kind of like want to pass this 9 back here, I better check. You know what this means? This means that both G and H are waiting on E. E has more than one immediate follower. Oh, now, so I need to check the start times on both, because G has to start at the latest in 12 days, and H has to start at the latest in 9 days, and I don't want to delay either of them. I'm trying to figure out when I have to finish E. Therefore, to not delay either of them, I pick the smaller. It was my sort of right in my instinct to pass that 9, but I could have made a mistake there if I did not check this, because you always want to pick the smaller. If there's more than one follower, you don't want to delay anybody. Okay, 9 minus 3, the late start time for E is 6. And that reasoning we went through just then, that is known as the late finish time rule. The late finish time for an activity is equal to the smallest. Notice now we pick the smallest. the smallest of the late start times that immediately follow it. Oh, all right, now we're almost done. We only have 2 other ones to fill in here. Let's see, B only has H following it, so there's a case where, you know, H has got to start at the latest in 9 days. Yeah, that can just become B's deadline at the latest. 9 minus 2, B has to start at the latest in 7 days, although you have the option of starting it as early as right now. And then now we only have A. Okay, oh, A is another example of a task that has more than one task following it, meaning that these tasks, they're all waiting on A, so we have to review them. Okay, D has to start at the latest in 12 days. C has to start at the latest in 10 days. And E has to start at the latest in 6 days. Given this choice, pick the smallest. We don't want to delay any of them, so we'll have to finish up at the very latest in 6 days. 6 minus 6 is 0. And I'm really glad to see that 0. Why? Because once I find my early start, early finish times, and then I turn around and I find the late start, late finish times, by the time I work my way back to the starting node, at least one activity attached to the starting node, the late start time needs to be 0. It needs to naturally result in 0, like A just did. If that doesn't happen, it means that I have messed something up along the way and I need to go back and find out where I made a mistake. But, oh, good, A zeroed out. Oh, now wait, those are the late start, late finish times, but we're trying to answer that question. What is the completion time of the project? Oh, wait a minute, we did that, 17 days. Oh no, the first question, what is the critical path through the project? The critical path through any project is the set of all activities that have 0 slack. You say, yeah, okay. Oh, and how do you calculate slack? Slack is the difference between, for instance, the late start time and the early start time, or the late finish time and the early finish time. So if slack is 0, that means that the late start time must be the same thing as the early start time, and the late finish time the same thing as the early finish time. Oh, you can see the critical path now. Look for everywhere that those timings match, like A 0606. Oh, wait a minute, and then down here E, we got the same thing both times, so to speak. H, I, and J. And now let's again another check on my math. This needs to be at least one path. A path is any route from start all the way to finish. Let's check we have a coherent route. From the start you can get to A, and from A you can get to E, and from E you can get to H, and from H you can get to I, and from I you can get to J, and from J you get to, oh good, yes. There is the critical path through the network. We could summarize as A, E, H, I, J. There is the longest path through the network. There is the path that happens to be equal to, if you add up the work along that path, 17 days. There in the highlight pen is the reason that the project's 17 days long. Oh, all right, now we at least got that first part of the scenario finished. What are the other questions? Okay, next question. What is the slack in task F? Oh, this isn't going to take very long. Slack, like we were just saying, is, for instance, the late start time minus the early start time, or your choice, the late finish time minus the early finish time. You had better get the same answer. Well, let's just go back to my work. Okay, where's F? F's right there. Late start time 13, early start time 9. Late start time 13, early start time is 9. Late finish time is 15, early finish time is 11. Do the subtraction in both cases and we get 4. We say, ah, there's your answer. The slack in activity F is 4 days. All right, and that one's done. How about this one? Suppose the project's been started. Okay, what is the longest you could delay? The longest you could delay beginning work on activity A without delaying completion time of the project. Oh, that's just asking for that. Now see, delay, late, beginning work, the late start time of A. This question is just asking if you recognize another description for the late start time of A, because that's what the late start time of A is. It is the longest that you could delay starting on A without delaying the project. All right, well look, that's right there. That's the late start time. It's 0. Oh, yeah. That's actually the answer. 0. Or you can't delay. You must start right now. Actually, this question said that you had already started, so you must have actually already started on A. But at any rate, that is asking for the late start time of A, and that is 0. All right, now there's one last question associated with this scenario. Suppose someone tells you they could get, okay, they're talking about activity C, done in 1 day instead of 3 days, because that's what we were working with, that you're planning on. Of course, they expect a bonus. What is your reaction? All right, well, you can consult the network if you want and look at C. Remember, we were planning on it being 3, and they're saying they could do it in 1, but they want a bonus. What is our natural or most rational reaction to that? We're not interested. You say, well, how do you know that we're not interested? We're not interested because it's not on the critical path, and that's really what this question is asking, is if you recognize the difference between the critical path and non-critical path activities. Not interested. Not a critical path activity. Well, what's so special about being on the critical path? Oh, what they're proposing, right, they could get it done in 1 day, is also known as, good keyword, crashing. They could get it done for a shorter amount of time, but crashing a non-critical path activity doesn't do anything for the project. It does not shorten the length of the project. Or another way to state that exact same principle is to shorten a project, and one assumes that's why you would be interested in paying somebody extra to do something in a shorter amount of time. To shorten the project, you must shorten critical path activities. C is not one of them, so that is why you're not interested.